the camera.
Right. All right. Well, thanks y'all for being here today. I'm Clinton Heider with the Center for Research Computing. This is my colleague John Mulligan, also with the Center for Research Computing. We're here to talk about virtual machines and a little bit about the research data storage options that we have, but primarily going to be focusing on sort of virtual machine concepts and different deployment options. I'm a little ragged today, but my voice, so bear with me. Mostly we're going to be doing kind of more hands-on examples and applications of this rather than dwelling on the sort of the kind of theory behind virtualization, but we are at least going to revisit some basic concepts. When we're talking about virtual machines, you know, the way I like to describe them, I mean, there's a sort of a more formal definition, which is a logically distinct computer with its own operating system, memory, CPUs, which runs inside another larger computer. That's called a hypervisor. But the way I like to think of it is that a VM is sort of like a simulation of a computer that runs inside another computer. And the way that this works is by creating virtual devices inside what they call the host operating system, which is the main piece of hardware behind it. And then those virtual devices are presented to the guest operating system, which runs inside the host and uses the assets that have been provided to it by the hypervisor. And here's my picture of hopefully a good representation of what I just described, where you have a physical server, and this could be very large. I mean, these, for example, in our system, in our ORION system, which I'm going to talk about later, a single hypervisor would have 64 cores, hyper-threaded, and 256 gigs of RAM. So it's a fairly large system. And it runs its own operating system and just sort of sits there and doesn't really do anything else except run this piece of important software called a hypervisor. And the hypervisor allows these physical devices to be partitioned and virtualized and abstracted, if you will, in such a way that they can be combined with disk images, which contain operating system configurations, and essentially this is what you would have on a physical disk drive like your laptop, for example. It combines them together and creates a VM which uses virtual devices and runs its own operating system and runs its own applications and services. You don't run applications and services out of this piece. This is logically and physically, in a way, physically distinct. The actual services run up here. And this is a really powerful model for a number of reasons, and I'll talk about why on this slide. And the biggest reason that people started using virtualization was to manage costs, because you can get a lot more versatility and utilization out of a large system instead of having multiple departments, like if you were running in either a university or environment, academic environment, or a business environment. You have all these different groups that need servers. They need, I need a web server for my department. I need a database server for my department. I need this and I need that. And everybody would stand up isolated physical hardware to do those tasks. And then when they didn't need them anymore, they would just sit there and be unutilized. And so virtualization technology allowed people to contain those things within larger systems and allocate the components out in a dynamic way so that you can reuse parts of hardware that were already there. And it became a pretty effective strategy for commercial IT shops. And they also began to develop ways of improving reliability, because this would allow you also to have multiple hypervisor machines, and you can migrate virtual machines across them. So what you can do is you can cycle through a number of different virtual machines, move your virtual machines from one hypervisor to another hypervisor if you need to put through maintenance or do work on that particular hypervisor, like you need to apply patches or you need to replace a network component or something like that. And you can do that without really suffering a lot of downtime because you're essentially moving a virtual machine from one host machine to another machine. And in some cases, you won't even have any interruption of the service layer. It also allows you to manage complexity. If you go back and look at this part with these images, these VM images are just files at a very simple level. They're just physical files that sit on a disk drive somewhere. And files are really easy to manage and make copies of. And you can retain their state, and you can do checksums, MD5 on them to verify that they haven't changed. And so one of the things that's really powerful about this is that you can clone virtual machines very easily from like a base image and then make changes on top of that. So you don't have to reinvent everything from the beginning every time that you start again. And the other nice thing about it is that the virtual device drivers that are created in the hypervisor layer here, these virtual devices are uniform and consistent. And so unlike a system where you may have several different generations of physical hardware in your data center or in your lab or whatever, and you have this kind of network cards and this one, and it needs a special driver, and then you have this one has a particular type of disk drives. This other one has a bunch of weird BIOS options or whatever. You don't have to worry about any of that stuff with virtualization because it's all been made into a homogeneous and reusable form so that there's a consistency of the way that the operating system views all the devices. And all of this combined allows organizations to have a lot of agility to be able to react to things quickly. You don't have to buy new hardware necessarily to do a deployment. You can say, well, I've got some spare capacity on this hypervisor. I'll spin you up a couple of VMs and you can play around with some new software. You can experiment and test. You can set up test environments that are very consistent, that are essentially duplications of your production environment. This is a really powerful thing in IT when you're trying to manage all of these different issues across different hardware platforms and everything else. So when you combine this with the fact that we now have this massive availability of resources over the internet, a bunch of different companies realized there was money to be made by essentially offering these virtual machines over the internet, and that's essentially what cloud computing has become. The two biggest providers at least that we've worked with are Amazon Web Services. These guys are the 300-pound gorillas, or 800 pounds. Is it 300 or 800 pounds?
It's a big gorilla.
It's a big gorilla. This is a 300-pound one. It's like a baby gorilla. AWS is extremely sophisticated and has a lot of different options of ways to manage virtual machines and other sort of virtualized resources, abstracted resources that you can combine in different ways to make some really powerful applications. And these are usually run, in large data centers around the country that you don't necessarily know where they are. They don't really want to advertise that information. They kind of keep that quiet. But the idea is that you can quickly get up and running in these environments. You can spin up VMs, you can spin up storage. It scales up easily. There's a lot of pre-configured application stacks, like if you just want a WordPress instance or you want to run, a machine learning AI stack. They have these things pre-configured for you, so you don't have to do a lot of the integration work yourself. And they also have multiple regions all across the country and in other countries as well. And some of them have a very sophisticated edge location for delivery of content, large amounts of content really quickly to avoid latency and things like that. But the redundant data centers are really nice because you can have multiple VMs in different regions and different areas, different what they call availability zones, so that if one of their data centers gets knocked out by some kind of a natural disaster or something like that, then it can fail over to another region or another availability zone. Now the disadvantages are that you can't really, it's very difficult to predict costs. They give you tools that let you do this, but they're, it's very, very hard, I think, to get a real idea of how much money you're spending until you sort of get in and commit to it. The data transfer costs out usually is where they charge you, is not to put data in, but to get your data back out. So if you have a really popular website that's downloading a lot of data to, or images or something like that to end users, then you're going to get a pretty steep bill on that. There are issues about privacy. Different rules apply to data custody in different countries and different zones, so you have to be aware of those kinds of regulatory issues. Like if you store some of your data in a different country because you want to be able to serve customers in that country, for example, then it can get complicated with some of the regulatory requirements. And the other thing is, if you've already got a lot of your own infrastructure, like Rice has, we have our own data center, we have our own data center personnel, we have a lot of computing equipment of our own. We have a pretty powerful and we network with a lot of capacity, and because of that, if you move everything to the cloud, it makes a lot more sense if you're a startup. It doesn't make maybe as much sense if you already have a lot of equipment and a physical plant that you're already running. I want to talk really quickly about some of these emerging cloud technologies. That type of cloud environment to deploy VMs gives some special advantages that you can use. If you, for example, don't want to have to run your own database and do all the administration, you just want a database instance, they offer applications as a service, like a pre-configured database. You don't even have to worry about the operating system stack or any of that. They also let you do things with containers, which are sort of isolated programs that run with their own environment contained inside of it. It's almost like instead of like a virtual machine, it's really more like a virtual application environment. There's a couple of different popular ones. There's Singularity and Docker, and they sort of pre-bake the cookies for you. That's John's. I stole that from John. So, so for very highly complicated application environments, you can kind of get it working in a Docker or Singularity instance, and then run those instances at scale in the cloud. Virtual private clouds are essentially a way of carving out your own network and your own resources that are logically isolated from other customers in the cloud. And you can actually connect your own infrastructure into it, although that costs money. And as I mentioned earlier, with the different availability zones of these cloud providers across the country, you can get a lot of advantages with high availability, because you can have multiple facilities that run instances with a load balancer in front of them that can detect when one instance is down and redirect traffic to a clone of that instance running in another data center. And then one of the most powerful things is the automatic load balancing and scaling, where you can essentially be able to detect when your systems reach a certain level of capacity. For example, if their computing capacity is going up above 80% utilization, then you can actually detect that and spin up new instances and put them behind a load balancer to expand your capacity. And then when those triggers go back down, when they resolve, it can spin the instances back down again. And the way what that results is that since you are paying for the amount of time you're running on the given CPUs, this allows you to scale your workload dynamically, so you're only paying for when your systems are being utilized, as opposed to spinning up machines and just leaving them there and having all this spare capacity and paying for it. So those are some of the advantages that you see in some of the things that virtualization allows you to do now, especially with our increased network connectivity. And at Rice, we also have a fast connection to some of these services through through our I2 connection, which we have a fast lane into a lot of these cloud services, which makes it nice. But we do offer our own private, which is really what we want to talk about today, and give you guys some examples of use cases. We have our own private cloud, which is a virtual machine pool that we operate. It's in our data center. And it's intended for pre-configured research application images, like research workshops that require a bunch of identical machines to be spun up. Web portals, we're going to show examples of web portals. And it's a way you can also quickly add sort of ad hoc computing resources, and John's going to give a great example of that as well, without having to go out and buy a machine, right? And it's also good for like test and build environments where you just want a place to play that you're not going to really hurt anything. It does have a cost recovery, but it's very competitive and it's sort of a fixed amount. It's very easy to predict your cost because it's basically, if you have a VM that has 4 CPUs and you run it all year continuously, then you're going to get charged 4 times 40 is $160 for that whole year. You do have to have a research faculty sponsor, and you have to apply for an account. And there's places on our website where you can do that. And right now, we're only running Linux flavors. In theory, it's possible to do Windows, but we haven't really had any demand for that yet. We have a bunch of pre-built images so that there are things like MATLAB. If you want to run MATLAB, you don't have to go out and install it yourself. We also have Docker. Coming soon, we're going to have Jupyter, the Jupyter Notebook, and hopefully a WordPress.
No problem.
A WordPress stack. We're working on those so that we can spin these things up quickly and easily. And I don't know if y'all have heard of like the whole 5.9 concept of high availability and reliability, but it's basically how many percentage points, 99.999% uptime and so on. There was a joke in the research computing community that we don't do 6 nines, we do 9 sixes. Which is not really fair, but the point to be made here is that this is not really a high availability environment, and we're not a 24/7 support shop. And we also don't have some advanced features like VPCs and load balancers and auto scaling and all the things that you can get in the cloud. But it's inexpensive, it's easy to get access to, and fairly flexible. And if you're interested in other ways of using virtualization and VMs and some of these types of resources, there are some other approaches that we have besides the ORION network. And one of those is Exceed, which is a consortium of academic and research computing powerhouses that pool their resources and allow you to apply for allocations. And it's basically like applying for a grant. And they have a special, they mostly do HPC, like big clusters, and you go and you run your jobs on the clusters. But they also have a system called Jetstream, which is essentially a kind of a private cloud, a research cloud where you can get VMs to do different things. If you are interested in an Exceed allocation, and you want to, we have what we call campus champions. I am one of them. There are people in our group who will help you prepare for, for a grant for getting a research allocation, and help you put together your proposal and give you some guidelines. We have a lot of a really experienced campus champion who's gotten a lot of people on these resources. And I already mentioned AWS and Google Cloud. They're commercial providers. They can be pretty expensive, but they do offer free trials and educational allocations. They don't last forever, but they're good at least to kind of play around with and kind of get used to the system. And then we also have a lot of other services, like if you just want to blog for your lab or a blog for your group and you don't really need anything special, customized or anything like that, or you just want like a collaboration space that's on the web, we have other tools. So, we have Ricebox, we have G Suite, we have blogs.rice.edu, and you don't necessarily need a VM and all that overhead to deal with that. So you kind of have to think about, do I really need a VM for my research or for these things that I want to do in my research group? Well, you may not actually need that level of customization. You may be able to get by with just some standard services we already have. And then I think that's all that I have to say at this point about the sort of the background of it. And what we want to do now is get into the practical aspects of how you use our ORION system. And then John and I are both going to go through some individual use cases and examples that we've come across since we deployed this system, which was, it hasn't been in production that long. I mean, it was basically
late spring.
Yeah, late spring when we started getting people in it. And you know, we've had a lot of success with it. It's been very useful. So the first thing I want to do is pull up the ORION console and you just open up a web browser because it's all browser based. And we're going to go to orion.crc.rice.edu. This is a little portal that just asks you for NetID and NetID password.
You do need an account.
You do need it, yeah. We need to turn it on for you, but it's tied into the NetID identity. I'm in admin view. I need to go to my cloud view, which is what most users will see. Right here, what you see is the dashboard of the system, and it shows just kind of a high-level overview of the different virtual machines that I have allocated. This right here shows that I have 2 VMs that I own. There are 7 that I have group admin privileges on. Because I support this, I have some additional stuff that you probably wouldn't see because I'm in a support role on this particular product, but still gives you a basic idea. It also shows that I have 1 VM running right now, which I'm going to use for a demonstration later. But if I want to make a new VM, let's say I have a simple MATLAB problem that I want to solve, and I don't want to run it on my own machine, or I want to run several iterations. I want it to run unattended, for example. I'm going to just click that plus and create a new virtual machine. Now, down here you'll see all these different things. These are all templates. What we call a template is a combination of a set of CPU and memory resources and a disk image that has some pre-configured operating system and software on it. And these templates are available to me, and I'm going to have to go find the one for MATLAB. That takes a little digging because there's a lot of them out here. Let's see, is that the... Yes, this is a good one right here. This was running a fairly recent version of MATLAB. So I'm going to give my VM a name. I'm going to call it MATLAB or ML1. And then I'm going to say I want to use this template. And what this is going to show now is the capacity of the system, which is already sort of pre-configured for you. This VM is going to have 4 CPUs, 16 gigs of RAM. You see right here that it's using the CentOS, which is a Linux distribution that has MATLAB, and the GUI indicates that it has a graphical interface on it. Not all the VMs do. Some of them just give you a command line interface. Some of the other things to note here, this persistent switch up here is a source of some confusion. Essentially what that means is that if you destroy this VM, the image behind it, the disk image behind it, will still be preserved. But destroying a VM is very different from powering it on and powering it off. We'll talk a little bit more about that later. So I have everything I need now. I've got my image. I've got my the CPUs and memory assigned. I've got a name for it, and I'm going to click create. And one of the things that's a little bit interesting about this is figuring out, now this thing is running, right? How do I actually get into it? And it's still deploying right now. If I click on it, you'll see that it's showing me the different stages of where I'm at in my deployment. And it gives me this number right here, 10.134.196.24. That's the IP address of this machine. And that's the way that you connect to it. That's its address on the network.
On the Rice network.
On the Rice network, that's correct. This is a private address that's visible only inside the Rice network. And so typically the way you interact with these types of systems is through a SSH terminal console. I have one up here. I'm going to get a new one. And I'm going to use the SSH command.
Can you blow your text up?
Let's see. There we go. There's my IP address. I'm going to tell it my username because it's tied to my identity on the machine is tied to my net ID. That's still deploying. Let's see. Let's see where it's at. Still going. This is the virtual console for the machine. So if you imagine that it was a physical machine and you had a monitor plugged into it, this is what it would be spitting out on the monitor at this time. So there's a lot of junk, but eventually it'll say that it's bringing up the network, and when it does, then I'll be able to connect to it remotely. Oh, I've got an old key in there. So let me explain another thing about accessing these. Actually, I'm just going to delete that file. I've been to this IP address before. So now it's going to ask me to enter my key in and permanently add me. And now I'm logged into my MATLAB instance, which is called ORION-196-24. And you can see that I'm logged into a Linux host. Now, how did it know who I was without me providing a password? That's an important step when you're doing a it's got there's my desktop in Linux. It came up finally. How I actually get in remotely is configured in my settings, and there's this update SSH key option that's available under my user settings. This is probably the most important technical piece of information that you might need to know if you're going to use the ORION system. The way that we authenticate users into the system remotely uses an SSH key pair, which is a cryptographic standard that allows us to have a secure connection, an encrypted connection between your laptop or desktop or wherever you're coming from and into the remote host. So what you do is you create a key locally, and there's a process for doing that I don't want to demonstrate today because it takes a little bit of doing, but once you generate this key, you put it in here. This is your public key. You have your private key on your laptop in your system, and you don't let anybody know what that private key is, but it generates a public key that's tied to the private key. You put this in the ORION system, and when the ORION system spins up your VM, it puts this key in a special place on the VM so that it knows who you are. And then when you authenticate with your private key, the encryption and decryption process matches, and it allows you to log in. So this is this SSH key is essentially the mechanism by which you gain access. Now you can go in the machine's console over here. If I go to my view where I have all my virtual machines running, there it is ML1, and I go to this little icon right here, this little blue icon is the screen, and it'll take me to the screen, and then I can actually go in and open up a terminal here. I'm not really a GUI person, so I'm not going to use this to do the next part of my demonstration. I'm going to use this remote console instead. Now, one of the things that's cool about this is you can spin up these instances and tear them down, at any time, and you don't your data, once you shut it down and if you destroy your VM, any data that was on it is gone. And the other thing about it is that these virtual machines don't have a lot of disk space on them. When you use a df command, which shows how much space actually, oh, this is a pretty big one. This one's 24 gigs, but it's still not a particularly large VM in terms of disk space, available disk space. And you really don't want to store your data on a VM inside this environment. So what you really want to do is you want to be able to access an external data store that you can use with other computing resources. And that's what our RDF, or Research Data Facility, can be used for. That is a network appliance that you can map from your workstation. You can map it from one of these ORION VMs. You can, as long as you're on campus, you can get to it from Windows, Linux, or a Mac very easily as a shared network drive. I'll talk a little bit more about it at the end if y'all have questions or you're interested. There are subsidized allocations available for research faculty, and then you can buy more if you need to. But rather than get too far into that, because it's kind of boring, I want to show how to actually use it from inside the VM. This one, I just want to make sure I have this. Yeah, this one already has an entry that allows this magic text down here, which you probably can't see because it's down too low. This shows that this VM is pre-configured to be able to access our RDF data store. And to do it, you just have to type mount/RDF. And it's going to ask me, whoops, oh, sorry. MNT RDF is what they want us to use. Then it asks me for my password. Now, this is my NetID password because that's how we authenticate our access to our storage. I'm going to try to move this up a little bit so we can see it better. Now if I run my command to see what systems are mounted on what file systems are mounted on the machine, you can see right here that I now have access to 242 terabytes. Fill it all up as fast as you can, right? But I don't really have all that much storage out there. I do have a little MATLAB program though in my directory. And it's called par Monte Carlo pi.m. I'm going to show you the contents of that. And this is a really simple MATLAB example that uses a sort of a statistical for loop to estimate the value of pi. And it has a cool command called parfor, which allows you to run iterations in parallel using multiple cores. And this system has 4 cores, and if I can get this to work right, then what happens is that it'll go out and run this iteration, this simulation of, what is that, 10 million times to get hopefully a fairly accurate representation of pi, and it will spread those iterations across the full 4 processors that are available in this machine. If you remember when I set it up, it had 4 cores in it. And it does some math, which I don't really understand because I'm not really a math person, I just pretend that I am. And then it'll spit out pi at the end. I'm going to run MATLAB. Let me get this out of my other. This is my little command here. Rather than have to type it. I'm going to tell MATLAB to run without a graphical display and to try to run my code, and we'll see what happens here. In the meantime, I'm gonna log in to my machine one more time. So I have another shell on it. It's working. So what it's doing is it's now setting up a parallel pool of worker threads to do my calculations, which if I look over here, it's still thinking about them. It's starting to spin them up. It's starting to spin up the worker threads. You can see
So
which
Clinton's
one-
logged into the same machine twice from 2 different terminals.
Right.
And one is running MATLAB, and the other one is monitoring the usage.
So each one of these is a little worker thread, and I think they even identify themselves. It's kind of hard to see again over there. Yeah, MATLAB helper. Oh, he's doing something over there, and he's about to print out my approximation of pi at the end. 3.1419. He used 4 cores on this machine to statistically estimate pi using MATLAB from the command line. Now, if I wanted to, I could run this, dozens of times and then come up with a statistical average of these to, get a good idea of what we think pi is. It's a really simple example, but it gives you an idea of how you can use the power of these virtual machines to do ad hoc calculations, to run simulations. You can do this on the clusters too, but if you just want something to play around with a little bit, the VMs work really well for that. And let's see, let's go back now to my list of, I want to show you about undeploying versus terminating. And so now we're all done with this MATLAB instance, and we don't need it anymore because we've got pi. We figured out what pi was because nobody knew until now. And what I can do at this point is I can just turn it off. This little power off button. It's kind of hard to see, but what this actually does is it takes the VM resources down, and it frees up the resources that are being used by it to be utilized again by other people who want to use it in the system. Now, if I use a trash can, it actually destroys the association of the VM, and it takes the image file that's been copied in the background and it discards that as well. If I just undeploy, then I can go back to my VM and restart it again. It'll save it out in my list of VMs, which you'll see on the dashboard over here. So you see, there's my VM is still there, and it shows it's in a state of being undeployed right now. And then eventually it'll show it as undeployed, but you can just redeploy it again if you want to without having to go through the steps of configuring everything and adding in whatever software packages and doing bringing your software in and all that kind of stuff. So if I don't need it anymore though, which I actually don't, and I go back to my dashboard, it's still powering off. It's taken a while. Once it's powered off, I can actually hit the little trash can icon, and then that will destroy the VM and clear out any of the data that was associated that's locally on the VM. But my RDF share, which I can also access from my Mac, could, for example, have the output that from this program sent to it, so that I can retain that on the RDF. I can retain my results on the RDF without having to worry about whether the VM is still there or not. So that's just one example of this. I think we'd like to move on with a couple of other ones. John, you want to talk about Harvey memories?
So, one of the uses of having these VMs with all of these different resources and the RDF on the back end that they can connect to, and that's what Clinton was showing you earlier, is that we can, if you ask us nicely, give you a public IP. This one's working. Oh, it's the other one. The other purple. Okay. We can give you a public IP to make this thing available from somebody's home computer as a website. So you could set up a software stack in order to serve up content from the this would be on the VM, so that people can access your data as a web application. Our pride and joy right now for this is Harvey memories. You might have recalled, I think Mr. Provost had that call go out for Harvey-related initiatives, and some people at the library decided that they wanted to make a collection of and Caleb McDaniel in history, and some people at U of H. They all teamed up and they made a website that allows people to contribute their own Harvey memories to I think this is running on Omeka. Yeah, it's on Omeka, and it's like a super souped up version of Omeka that they've highly customized to be able to allow people to upload tweets, upload images from their phones, and all of this to this public database of memories from Harvey. And so what they've actually allowed is for people to take all of this content that they've got and dump it, in a manner of speaking, into Rice's servers. And then, through the web application interface, to access it as web content, right? This, basically, I mean, you saw how much space was available when Clinton showed you the RDF share. Like, you can put a lot of different iPhone photos, like, in that storage system. And it comes pretty cheap, like Clinton was saying. And serving up this content, when you compare it to Google and AWS, we have found through terrifying example, accidentally over the last year, just how expensive Google Cloud Computing can be if you have a website that you build that somehow becomes slightly popular and has any amount of data that it's serving up to people. So we have a professor who Clinton and I helped to set him up on Google, and it was $300 credit, and he burned through it in about 8 months because he actually built something people wanted to use, and now he's being penalized for actually doing a good job. So that sucks, and we're going to try to find a way to move him on to Orion. But the difficulty, as I'll get to in a minute with Luis's example, thank you, is that these sorts of web applications are really, they take time to maintain. It's cheaper to run on Orion and on the RDF, except that it's not. Like, Harvey Memory's got a lot of money in order to be able to have staff time, in order to be able to have the overhead of developing this stuff, in order to be able to go out and do field interviews and everything. So there's actually a lot of highly competent people who are doing a great job at making this website possible. And if you don't have a team of web developers, or if you don't have a dedicated person who knows how to do this all the time for you, and currently we can't supply that service at the CRC, then you're going to find yourself sort of hanging out in the wind with a website that's hard to secure, right? A website that's hard to maintain. Because the difficulty is, if you're running a web application on the Rice VMs, you're just a massive target that hackers want to get at, because there's a lot of computing resources that they could take over if they got inside of the system. Don't worry, we won't let you get yourself in trouble that way, but for the time being, the moral of this story is that it's cheap, except that it's not. right? There's overhead that goes into making these things. May I show you a website, Luis?
Yeah.
Okay.
I should have it in there.
You do. All right. Luis had a website that we helped him to stand up on Orion and added a bit of extra functionality to, which is a database of Latin American films that runs on Drupal, as opposed to Omeka or WordPress. So the sorts of websites we want to help people build are data-driven websites. If you want a blog, OIT has a great service for that. But this isn't a blog. This is a database with a web interface that allows people to upload information, to embed video links. The beauty of Luis's site is that these videos, right? The big question is on a website that's dedicated to films, you want people to actually see the films. So we allowed for some video embedding. The difficulty was that you start to put full-length video files on the RDF and run it through this, and you're going to get into a lot of problems with just taking up space and having to pay for it and all of this. Fortunately, there's a thing called YouTube, so we had them do it for us for free. And so Luis has a student who's clipping films according to the listings that are being given on, say, Mise en Scène, where somebody can show an example from a film and describe it, and then embed the clip from Luis's YouTube account. So what's super cool about this is that we've got this situation where it's a media-rich website running off of a database that sits in Drupal, and because it's on Orion in our VM cloud, we can back the site up at any time by freezing an image, so that at any point in time, we can have a backup to fall back to in case anything goes wrong. We should do that, by the way. And we've got this rich video content that's coming from the web, but the database is relatively small. It's just text and hyperlinks to these videos that it then translates into video embeds. So the overhead is not that great. Luis's site doesn't even have an RDF share attached to it. Because what he's got on there is less than a gigabyte. I mean, it's a small website that it's running. And so, built in this way, this thing is super lightweight, and I could see this thing being made public at some point in time. The downside is we've kept it, if you're on Rice campus, you can go see Luis's website. If you're not, you can't, because we're a little concerned that we don't actually know enough about technically how Drupal works. We are hiring people who are going to be application developers who are much better at this stuff and some security specialists, but for the time being, I don't feel comfortable making your website vulnerable to potential hackers. And so it's a great website. More content is being added every day. Go learn about Latin American films. We'll share you the link. But it's a lightweight VM that's serving up web content on a private IP address. Does that make sense, the distinction between these two projects? Okay. What was our next example?
The next example, well, I think we can probably skip over that one because it was, I think we should maybe talk about your computational examples.
Okay. Okay, great.
Yeah, because the
Here.
RDF integration we kind of already covered.
That's my laptop. So those are two web portal examples, but I want to show you guys sort of a variation on what Clinton was showing you. Basically, let's imagine that you're a humanist who has taught himself just enough computing to get himself into a lot of trouble. This is an autobiographical story. I go to So, as Clinton was saying, you can, this is the RDF share mounted on my computer, right? So this appears as just another network drive, right? So it's another hard disk, like tied into my computer. So now I'm in here. Let's open up a terminal. And I want to show you, I'm actually going to need 2 terminals for this job that I'm going to show you. Raise your hand if I've bored you with my Shakespeare co-citational example. Yes. Clinton's ears have bled from this thing. I won't give you the painful details, but essentially, Da Vinci is one of our soon-to-be retired, but personally, my favorite supercomputing clusters. It's going to be moved over to NOTS. I am a fan of Da Vinci in its current build. It's a sad day for me. I'm going to log into my Da Vinci account right now. The way that supercomputing works is not structurally dissimilar. So this is my home directory on Da Vinci, right? This is my home directory on the supercomputer. My work, so right now, there's nothing in here. Right, my work that finished last night on a job that I was running produced a shitload of databases, all of them relatively small. Taken all together, they amount to about 500 megabytes. And what I have to do is I have to combine them. There are about 72 of them. I have to combine them into 2 final databases. And how do I want to do that, right? So the example I'm about to show you is I've got a laptop. And my poor laptop should not be taking this overhead, right? My poor laptop could totally combine all of these different databases, except that I don't want to ship 400 megabytes to my laptop, right? Especially if I'm at like double trouble doing this, right? Because I don't want to go over commercial internet. So what am I going to do? I'm going to log into an ORION VM that is already connected to the RDF, because these guys are all on the Rice network. And I'm going to have my laptop orchestrate a series of moves. First, I'm going to take the files from Scratch to my home directory. Scratch is connected super fast to the nodes. This is where like your output files get written on a supercomputing job. I'm going to move them to my home directory. I'm going to move them from there to the RDF without them ever touching down on my laptop. The ORION's going to manage that. And then ORION is going to do a quick job where it combines all of the databases into some outputs using the script that I wrote. And you'll see that it happens pretty quickly. First, because ORION is fast. Second, because ORION is directly connected to the RDF. And it's not going to take up any space on my computer. So right now we're still in. All right, so right now we're still in Da Vinci. I'm going to, sorry guys. This is step 1. And I'm going to log into my VM over here. All right, so now in our current directory, all of our mini databases ready to be moved, right? Now I'm in my VM, and I'm going to say SCP, which, what does that stand for?
Secure copy.
Secure copy from a remote location.
It's like FTP, but with SSH encryption stuff enabled. Uses the same protocol.
Nice, thank you. So I'm going to do the same thing, but look, I'm in ORION right now, right? Like, this is my terminal in Orion, and I'm about to tell my Orion VM, okay, I want you to take these files and move them over to the research data share, right? My laptop is telling Orion to do it, but Orion is actually doing the work. So I'm going to kick off this transfer. I'm going to take everything in my home directory, all right? And I'm going to move it to all right, it's a bit of a trick. Here, I'm just going to move these guys. I'm going to take one of the batches for now. But first I need a home directory to put that in. There we go. That is pretty damn fast. That's 250 megabytes that just transferred over. Pretty cool, right? And now I'm going to, where am I? Okay. So now I've got this little program here, Shakespeare Concatenate, that's going to go and look for databases with those specific file names in that specific folder over on the RDF. It's all, I mean, it's all very pre-cooked. All of this stuff, it's baked into the code. Like you can see I've hard coded all of this shit in here. That's the path, those files that we're going to look for. It's going to take my input variables and use them to look for specific databases with those specific names and a specific subfolder, right? So it's a little crude, but whatever. And we're doing 14 and 50 is the output files. What's going on right now is it's taking these databases, one after the other, those 5 megabyte databases, shipping them here, putting them into a new master database that it just created, attaching them, deleting them, and then at the end, it takes the finished database and it moves it over to the RDF. So we will see this guy just got created, 188 megabytes. Right? That all got built in the RDF, in Orion, and shipped over after doing, after bringing 38 5 to 10 megabyte databases over, adding them to the master database that it made, and then shipping that back over and deleting and cleaning up after itself. And nothing touched down on my computer, right? What I just did runs just about as fast if you're just at home on a VPN, because I'm not shipping any of that data to my local machine. Does this make sense? So another use case for that is my supercomputing job a few days ago didn't finish, and I had 1 or 2 databases left over. So I tried to run this same process with just a little bit of a cleanup job, 1 node a piece. It turns out the supercomputers do not like running jobs with one process a piece. They really like you to do parallelization. That's what they're built for. And so the job sort of blew up on me. I'm sure there's a way I could have configured it to run, but I didn't want to rewrite my code. So it just shipped everything over to Orion, and I had Orion do it, and it finished in about 20 minutes, right? Again, it's basically like I needed just a little bit more computing power, than what my laptop had, and I did not want to burden my laptop with the file sizes, and I definitely didn't want to be forced to sit there and watch the terminal tick away. There's a dead roach there. And I did not want to sit and watch the terminal tick away. I just wanted the job to get done. So I set Orion to do the job, closed my laptop, and like a few hours later I checked back in, and you know, as predicted, all the work had already been done for me, right? Which is similar to how you run things on a supercomputer, except this is just sort of like, you know, this is smaller board. You don't need to go for the big guns here. One more example, a bit more fun. Just to show you that it's not just about computing. So like first I showed you web portals. Now I showed you a little bit of extra computing power. Now I'm going to show you a web-oriented program that I made that runs off of the RDF, but does not make itself publicly available. My use case was follow me on Twitter. I had a bunch of historical resources. I am a special kind of humanist who, like Mary Poovey, makes other humanists' eyes roll into the back of their heads. I work with historical databases. And these astronomers who I'm obsessed with, the Herschels, they, over the course of about 15 years, invented the practice of cosmology. They built these telescopes that run, they built these telescopes that look at a sector of the sky at any given moment. That's about a third, the diameter of the view window is about a third the width of your pinky, right? So teeny tiny. What they end up seeing, that changes the night sky. You don't look at a constellation, point your telescope at a strange object, and see it better. You're looking so deep into space that you actually don't know what you're looking at anymore. You become completely disoriented. And so they figure out, well, what are we going to do with this? We're going to start sweeping. We're going to do sectors of the sky, and we're just going to see what shows up. This becomes massively disorienting as a data gathering operation, because now all of a sudden you're seeing a bunch of stuff, and you have to be really certain that you know exactly where you're looking when you're seeing this stuff so that you can go back to it. The benefit is if you do the job right, people 200 years later can recreate it, because astronomical phenomena are the most predictable scientific phenomena ever invented. And so I had a student create an application for my Mac Mini that I bought, and is sitting on my desk. And anyone ever use a Mac Mini?
Yeah.
Yeah, so this is the sort of thing that you buy when you just want like a little bit of compute power and you don't really care if it's pretty, and maybe you buy a monitor for it, right? So think about it as like a bootstrapped VM, right? Or I mean like a, you know, a quick and dirty VM, right? So it's just a brick sitting on your desktop, right? And I got a cheap ass monitor, and we started running these simulations of every single sweep that the Herschels ran. And what I put on this VM was, I'm thinking about you when I'm telling this story. What I put on this VM was, a little Python script that started doing screen captures of this thing as fast as it could. It got about 5 frames a second when I was writing to local disk. I am still totally unclear as to why this is the case, but when I started writing to the network, instead, right, so I just mounted the RDF share here, and I had it write my screen capture images directly to my Isilon share, and it started capturing at 7 frames a second. So over the network, it was writing faster than it was writing to my local disk, which right? Yeah. Yeah, Jan, Eric, and everybody I told this to from the CRC is like, oh, that's cool, but we still don't know why. That's just to say the RDF is fucking awesome, and it's super fast, because that should not be the case. Or it says more about how much my Mac Mini sucks, I think. But you can say both at the same time. So basically, I had it run simulation after simulation after simulation in a row, right? And what we ended up with was about somewhere in the order of like a gigabyte subfolders of like sweep 1, sweep 2, and 30 to 40,000 high definition PNG files that then I had this guy on a constant loop checking. And so it was just constantly checking, and this guy was constantly writing. And he kept dumping into different folders all these images, and when he moved from sweep 1 to sweep 2, right? So it's writing here, and then it's writing to a new subfolder. As soon as it makes that new subfolder, this guy says, oh, okay, so you're done with sweep 1. Well, I'm gonna take sweep 1, and it starts adding up all of those images and turning them into videos. So while this one is running the simulations, right, it doesn't have the overhead to be able to do writing and reading and compiling. It would have slowed down the capture. So I just need a little extra compute power. So this guy here starts making videos out of the images as soon as this one's done with it. Then, as soon as a video is done being compiled, another thread on the same script goes and checks a database that I've got made custom. It is so weird what they think I'm associated with. So it goes and checks this database, and I've got it on my desktop just for illustration purposes. It's keeping track of all of my assets. So basically, I've got all these screenshots that I've built up that are tagged with the different sweep that it goes with. And that's what you're seeing over here, by the way, my screenshot library. All of this lives on the RDF, but this database sort of just keeps track of it. Then we've got all the different sweeps and the ones that I've made a data on. When a sweep is run and the video's been compiled, then it goes to upload it. When it's uploaded, it switches this byte here and says, okay, it's been uploaded, so it doesn't do it again. And then it says, oh, have I tweeted about my new video, right? Because it's really obsessed about tweeting about its YouTube videos. It's a bit of a social media diva. And then it goes and it flips this bit over here and records what the YouTube ID is, which is the unique identifier that you put at the end of your YouTube URL. So basically, what I've got here is Orion, like, on the one hand, writing all of these videos out of the images, deleting all of the images so that I'm not taking up extra space. It cleans up after itself, and then going and posting about these to YouTube and to Twitter, and then linking the tweet back to the YouTube video, all in one go, right? And I couldn't have done that running it on this. Running it on my desktop, sitting next to my Mac Mini, would have required that I never turn my desktop off, that I never accidentally close my terminal, right? But this thing, I just left this running for a week while this was running through all of its simulations that had a week worth to simulate, right? And so it's just some basic screen captures that this guy then turned into the most boring YouTube channel ever. But I didn't have to do it by hand. I would just check it every few hours and a new one would be up. And it would have 0 retweets, obviously, but so you got some background processing capabilities that you can kick off with these things by basically just strapping another CPU to whatever your workflow is, if you can think clearly about what your needs are. Is that helpful? Yes. And this is scalable too, right? I mean, like if I actually had like a lot of shit to go through, maybe I'd clone the VM a few times and have a few of them working to process the videos if the overhead were actually much greater. Cool? All right. Those are all our examples.
I think so, yeah.
Yeah.
I think, well, I did want to mention just briefly one other example that we had a faculty member, excuse me, recently, who he's in computer science, and he uses he works with computer languages, and he's working on a new programming language that he wanted to test some optimizations with. And in order to do that, he needed a group of essentially identical systems that he could run a whole bunch of these code simulations on simultaneously and be able to take performance metrics on them. And he decided, well, Amazon's too expensive. And he went out and allocated, I think, something like 40 or 50 Orion VMs, which stretched our capacity a little bit, but it worked out quite nicely for him, and he got a paper out of it. And it's an example of what we call a spiky workload. If he had to go and purchase equipment to do this, it probably would have been cost prohibitive, and then he'd have these systems sitting around, unused for months until he did another run. And so this is another way to think about why Orion might be valuable, is because you're only paying for it, you're only getting cost recovery when you're using it. When you're done, you can undeploy your resources and go back to using those funds for something else. And I think it was a really nice example of a way to get a whole lot of resources really quickly without having to do a whole lot of planning. The other nice part of it is that he was able to replicate an environment down to the finest detail, because he's basically using clones of a bunch of the same VM image. So he can propagate what he called these worker nodes across 40, 50 different VMs, just like that, by essentially cloning them. And then he has a completely discrete environment where he knows he has total control, and they're all using the same device drivers, they're all using the same memory configuration, they're all using the same CPUs. One of the things to point out about CPU allocations in Orion is that the way we have it set up is that you get one CPU thread per core that you request. We don't do what's called oversubscription, which you can do, where you create a virtual core in your VM, but it's only getting a slice of an actual CPU. When you get a core here, you're getting the whole core. So I wanted to point that out, and that was very helpful to him as well, because if he was getting a simulated core that was only a slice of a core, like a time slice, it would have completely thrown off his calculations, I think. So, but that's another example of how we can accommodate a spiky workload. Hopefully, when we get more hypervisors, which we're working on, we'll be able to supply even more capacity for these kinds of spiky workloads. So.
Yeah, we went a little over. Thanks, guys.
Yeah, we sure did.
I think we meet a student, but hey, nice meeting you.
Nice meeting you. Thanks for being
Fascinating.
here.
Thanks.
Nice to see you again.
Now you know how it
Thanks for
works.
coming.
It's amazing.
Yeah.
We'll meet soon.
Yes. Yeah, drop me an email.
Great meeting.
Nice to
Thank you
meet
so much
you.
for all of it.